Today we're talking about empirical formula, and this falls under a category with something called percent composition as well. So empirical formula first, and kind of along the same way at the same time, percent composition. We'll be doing a lab that kind of involves a little bit of both, and they're very much intertwined with each other, so it's hard to separate one from the other. Empirical formula did introduce that idea first, then you'll see how the two are connected to each other. So what's empirical formula? Basically, an empirical formula is if you take a regular chemical formula like we've been writing and using all year, and you simplify it down. So if you take an empirical formula for a common compound that can be reduced, that reduced version is the empirical formula. It's the simplest whole number ratio of elements in a compound. So I'll give you a few examples here and just show you how to take a regular chemical formula that you'd see in a compound or in an equation and turn it into its empirical formula. So down the left side here you see 6 kind of common everyday chemical formulas, and then on the right side we'll add their empirical formulas. So I'd encourage you to make a little chart like this in your notes too, so that you see a few examples and the ways of handling empirical formulas. The first one you see there is a formula for glucose or dextrose sugar, and C6H12O6 is a very familiar compound. Well, you can look at those subscripts 6, 12, and 6, and you can tell you can be reducing those by dividing them all by 2 or 3 or even by 6. So if you divide them by 6, you'll get them to their simplest whole number ratio, and that would give you the empirical formula, C1H2O1. Now the empirical formula is not the same as the chemical formula. You would never look at C1H2O1 and know that you're talking about sugar necessarily. It's possible, but there are other compounds that have that empirical formula too. So an empirical formula is simply a ratio, and it has uses in chemistry, but it's not nearly as useful as the full chemical formula, which is why we use those most. A few more examples, and then I'll show you more of what I mean by that. Sodium chloride, table salt, regular NaCl, can be reduced. Well, not really, because NaCl is already its simplest ratio. It's 1 to 1. So when we're writing the empirical formula, we typically would write it as NaCl or Na1Cl1. That's an example of a compound for which the empirical formula and the chemical formula are the same thing. You can't change it. You can't make it any simpler anyway. And whether you put the ones in there or not isn't terribly important. I'm going to ask you to put the ones in for the empirical formula, but it wouldn't necessarily be wrong if you left them off. Water, very common everyday compound in lots of our equations. H2O, that's as simple as it gets as well. So if anything, we could add the 1 and say that H2O1 or just H2O is the empirical formula for water. So those last two are examples where the empirical formula actually does tell you what it is and represents the actual formula itself. The next one on the list here is the formula for acetic acid, so vinegar essentially. And acetic acid is HC2H3O2, hydrogen and the acetate ion. One trick I want to show you here is that when you have H's in two places, for example, as we do in this compound, to find the empirical formula, you'd want to put those together. So that would really give you C2H4O2 by combining the hydrogens together to get the empirical formula, which you would get by reducing that. So C2H4O2, when we combine the H's, can be reduced down to C1H2O1. It's the same ratio as our sugar was in the first line, so a 1 to 2 to 1 ratio for sugar, for vinegar. Well, obviously you know sugar and vinegar aren't the same thing, and so apparently empirical formula is not the same as chemical formula. Knowing that two very different compounds have the same empirical formula gives you an idea of just sort of how limiting empirical formulas can be. And so they're usually not the end of our process, they're just sort of a stage along the way. Another compound, CH2O, would also have the same C1H2O1, or just CH2O as its empirical formula. So there are several compounds here in this list that all have that same empirical formula, and I choose those just so you can see that. The last one that's on here is calcium nitrate. Now, calcium nitrate is one of many compounds we work with that use parentheses when we write it. When you're writing empirical formula, you wouldn't want to use parentheses. We don't show parentheses in any empirical formulas, no matter how big and complicated it is. And again, without parentheses, we can't recognize a compound very well sometimes. So it's limiting to look at the empirical formula only. But if you think about what calcium nitrate would be without the parentheses, it would be 1 calcium, 2 nitrogens, and 6 oxygens. Well, that's a 1 to 2 to 6 ratio. You can't simplify that. So calcium nitrate, written as its empirical formula, really isn't simplified from parenthesis version on the left, but it is very different. We don't look at CaN2O6 and think it's calcium nitrate automatically, perhaps, because it's been changed from the parentheses version that we're used to. So there's some examples of empirical formulas from chemical formulas. What I want to do with you in our first kind of calculation and work with empirical formula is show you how we get it. Typically what you would do is take a compound, an unknown compound perhaps, or the result of a chemical reaction where you're hoping that you know what you've made and you want to check that you've made a pure compound or a pure product. Maybe you're manufacturing a pharmaceutical for a drug company or something, or you're manufacturing a chemical at any industrial plant for sale. We need it to be pure, and so they'll test it in a machine, various machines, and what it'll do is analyze the elements that are found in the compound. So if you put a drug or a compound into a machine, it'll spit out how much of that compound is carbon, how much of that compound is hydrogen or oxygen or sulfur or whatever it might be. The same thing would be true of, say, Olympic athletes being tested for performance-enhancing drugs, or any athletes that you see on TV who are getting suspended and so on for using drugs. A lot of the ways that they test that, simply by urine or blood tests, they put the compounds or they put the urine and the blood samples into a machine that can tell you exactly what's in it. And the way it does that is through this sort of math and process that we're going to look at here next. So under the sort of a guide of, or the guise of calculating empirical formula, that's the process I'll take you through with a quick example here. This is going to be problem number 1 from the practice page that I'll give you in class, or have already given you in class. And if you're not in my class and you're following along, you can just jot this one down. So let's say we put an unknown compound into a machine and it tells us that that compound consists of carbon, hydrogen, and sulfur. Here at the top of the screen you see those 3 elements listed. And not only that, but the machine tells us that there's 33.3% carbon in that compound, 7.45% hydrogen, and 59.3% sulfur in that compound. So those 3 elements, and that's it. It tells us the percentages, it tells us how much of each one there is then by percentage of the compound. Now just like with hydrates, sometimes with percentages, we're sort of assuming then that if we have a 100 gram sample, that those percentages would mean out of 100. In other words, the first step of doing an empirical formula calculation is to make that assumption that a percentage would be equal to grams in a 100 gram sample. And it really is. It's exactly what percentage is. So, for example, in problem number 1, it tells us that there are 33.3% carbon atoms in this compound. That means that if we had a 100 gram sample of this compound, that there would be 33.3 grams of carbon. So we can make that assumption for carbon, for hydrogen, for sulfur. There would be 7.45 grams of hydrogen, 59.3 grams of sulfur in this compound. We're making the assumption that we simply can make percentages into grams out of 100. So the next step is much like it was in our hydrate problems too. We take those grams, in this case we have 3 different elements, so we take the grams of carbon, hydrogen, and sulfur, and we convert each one to moles. Well, that means setting up basically 3 simple mole conversions, just like this: carbon, hydrogen, and sulfur. And I look up the molar masses from my periodic table, and I plug them in there to make a mole conversion. Now I want to point out one thing that's very commonly sort of mistaken here, and get you hopefully out of the habit of doing this. And that is with hydrogen. Hydrogen, we know, is a diatomic element when it's an element. In this case, though, remember, hydrogen is in a compound, so you don't treat it as being diatomic, as diatomic hydrogen is an element, because it's part of a compound. Just like oxygen isn't diatomic in water because it's part of a compound, hydrogen wouldn't be considered as a diatomic element in this unknown compound that we're trying to figure out. So with your molar mass for hydrogen on this problem, you use 1 gram of hydrogen, or 1.01 gram of hydrogen for its molar mass, for the element's molar mass within this compound. So if that's confusing, just keep in mind there are no diatomic elements in compounds as they exist, because they're not elements when they're combined with other elements. They're compounds then. And so in our example here, we don't double hydrogen's mass, long story short. So make these conversions, and you can make this division happen rather easily. And as always, keep significant figures in mind. So 3 significant figures on all of my masses. I should have 3 significant figures on all of my moles. 2.77, 7.38, 1.85, all 3 significant figures. And be labeling things: moles of carbon, moles of hydrogen, moles of sulfur. All right. So we've made our mole conversions. The next step is kind of like hydrates again. And if you haven't done hydrates yet, and you're watching this video out of order or something, then this is still pretty straightforward. What we need to do is relate these elements to each other in terms of how many moles we've got, and mole ratios are the answer. So the first step then is to calculate a mole ratio for 2 of those elements. Now, which 2? We got 3 elements. How do I know which 2 to choose? Here's the guideline that I'll always tell you to follow. Take the element that had the largest number of moles and divide it by the one that had the smallest number of moles. This is kind of like hydrates again. In our example, Okay, we had 3 different elements be converted to moles, and we had 3 different answers for our moles. You want to find the largest one, divide it by the smallest one, just like we did that with hydrates. And here, we want to round off our answer here, which that question mark represents. What is it going to tell me when I punch this into my calculator? Round that off to the nearest whole number, or you're allowed to round it off to the nearest half. So 2, 3, 4, 5, those would all be great whole numbers, or you could round it off to 2.5 or 3.5 or even 1.5. So our example then, hydrogen had the most moles, 7.38 moles of hydrogen, and sulfur had the fewest. So I'll set up my first ratio as hydrogen over sulfur, 7.38 over 1.85. And when I divide that out, my calculator tells me that that's a 4-to-1 ratio. I round it off to the nearest whole or half. In this case, it's 4. So that's a 4-to-1 ratio of hydrogen and sulfur. 4 moles of hydrogen for every 1 mole of sulfur. This should look familiar to a hydrate problem, which if you're in my class, you've already done by now. 4-to-1 ratio of hydrogen and sulfur, but that doesn't cover carbon. What about carbon? So that's our first ratio, a 4-to-1. The next step is one you may have to do many times on a given compound because there might be lots and lots of elements. But when there's only 3, as in our example here, we'll repeat the same process again, except now you use the second largest number of moles on top and divide by that same bottom number. Keep the denominator the same on all of your ratios. The smallest number of moles goes on the bottom for every ratio that you do. You want to keep that kind of as your common link. So carbon was my second largest number of moles when I made those first conversions, 2.77 moles of carbon. I'm going to divide that by the same 1.85 moles of sulfur that I used in the last ratio. So 2.77 divided by 1.85 gives me a 1.5-to-1 ratio. Now we're not going to round that up or down to 1 or 2. We're going to keep it at 1.5. There's 1.5 carbons for every sulfur in this compound. Now you're thinking maybe 1.5, that seems wrong. It's okay to keep halves here because we're going to see halves show up fairly often actually in empirical formulas. Once we've done that, if there's another element in my compound, I'd have to do one more ratio with sulfur on the bottom again. But because there isn't another element, I'm done with my ratios. I've got a 4-to-1 ratio and a 1.5-to-1 ratio. Final step then is to take those ratios and turn them into subscripts. So it's kind of like when we wrote our hydrate formula. For example then, we've got a 1.5-to-1 ratio of carbon to sulfur and a 4-to-1 ratio of hydrogen to sulfur. You can kind of see it here in the formula in the bottom left corner, a 1.5 to 4 to 1 ratio. 1.5 carbons for every sulfur, 4 hydrogens for every sulfur. So you can see both of those ratios sort of stored or visible within that formula. Now here's the thing. You should look at that and say 1.5 has never been an okay subscript before this. Why is it okay here? It's not. 1.5 doesn't work because this compound can't have 1.5 atoms of carbon in it. You can't have halves of atoms in compounds. It doesn't work. So what we do is what we did when we were balancing equations, and we sort of cheated a little bit to balance a tricky equation. We'd use halves, and then we'd double everything up. Well, we're going to do that here too. So double all your subscripts if you've got a half. If you've got a half, double your subscripts and make them whole. If those are already whole numbers, maybe if it's a 2 to 4 to 1 ratio, then you wouldn't need to double everything. But because there was a half in there, and that's not okay, we double everything. 1.5 becomes 3, 4 becomes 8, 1 becomes 2. And instead of 1.5 to 4 to 1, I've got the same thing, but twice as big, 3 to 8 to 2, C3H8S2. And that would be the formula for my compound that had the original percent composition data that started this problem out. So it becomes a problem that's a lot like hydrates. Convert your percentages over to grams. Just assume that percentage represents grams for a 100 gram sample. Then convert all those masses in grams over to moles of each element. Then find your mole ratios, starting out with the largest number of moles over the smallest, then the second largest over the smallest, and if you had more, the third largest over the smallest, and so on. And then once you've got all those ratios figured out, turn those into subscripts in a compound formula. Last question some students ask is how do we know what order to put the elements in? How do I know it's C3H8S2, and how do I know not to start with sulfur or hydrogen first? In the end, it's not terribly critical. There is a set of rules that tell us the order of elements that should go in a formula like this, but I'll say if they were in this order in the original question, in the original information, C, then H, then S, then go ahead and keep them in that order, then C, then H, then S. Carbon followed by hydrogen, followed by sulfur. Good rule is if there's carbon, it pretty much goes first almost all the time because carbon leads off most organic compounds, and lots of these are. Hope that makes sense. If not, see me in class or outside of class for some help, and we'll work on more. Otherwise, try one or two more examples on the page. Pick some that have 3 elements in them and see if you can figure one out. And remember, at the end, only double those subscripts if you've got a half. You wouldn't need to double it if you didn't have a half, because if you did, you wouldn't have the simplest ratio anymore. And we want a whole number ratio, but we want it to be as simple as possible. And this one ends with a 3 to 8 to 2 ratio. Can't get simpler than that without getting to halves. Hope that makes sense. If not, I'll see you in class. Thanks.